Section 9.7. Let's do some examples on Thevenin equivalent circuits. So we have a circuit that looks like this. The current source is given to be 2.45 amperes. Very good. And we are supposed to find the Thevenin equivalent with respect to terminals A and B. Okay, with respect to these terminals, we are supposed to find the Thevenin equivalent. So that amounts to finding the Thevenin voltage and the Thevenin um, impedance. Okay, so let's go about that. Let's try to find the Thevenin, VThevenin first. VThevenin is defined as the open circuit voltage. Okay, open circuit voltage looking into the terminals A and B. Okay, let's start. So solution, I'm going to make a few observations. Okay, I have forgotten to annotate this to be the Ix. Okay, now what is the value of Ix in terms of the voltage here? The voltage V20 ohms. Okay, if the voltage here is V20 ohms, clearly we know Ix is the voltage across the 20 ohm resistance divided by 20 ohms. Okay, so we are introducing a new variable V20 ohms. It's a variable. We will have to solve for that later. Okay, now if we apply KCL at this node, what is going to happen is there is one current entering, that's this guy, and two currents leaving. So KCL at node V20 ohms. So applying KCL, I don't know, I'm going to call this node N1. Okay, apply KCL at node. You see, all the techniques that you learned in chapter 4, steady state analysis, apply in sinusoid analysis as well. The only difference really is you're dealing with complex numbers, polar form, rectangular form here. Okay, all right. So when we apply KCL, the current coming in is shown as negative 2 angle 45 degrees plus the current leading down this branch is really Ix, which is V20 ohms by 20 ohms. So that part I'm going to write as V20 ohms by 20 ohms. So that really is Ix. Okay, that's the current flowing down here. That's Ix. Okay, plus the other current that is leaving is V20 minus the voltage here, which is 10 times Ix divided by J10 ohms. So I'm going to write V20 ohms minus 10 times Ix by J10 ohms. So that's the voltage dropped across this impedance, right? That's the voltage drop across that impedance, which happens to be an inductor. Okay, now we can uh, um, we can simplify this. All of this, the sum of all the currents at that node N1 should equal 0. Okay, it should equal 0. Now, what else can we do? We can do a little bit of mathematical analysis. I can write this as V20 ohms by 20 ohms. Okay, V20 ohms by 20 ohms plus V20 ohms minus 10 times, I'm going to replace Ix by this. Okay, 10 times V20 ohms by 20 ohms, okay, by J10, okay, by J10. That equals, I'm going to take this to the other side, okay. I'm going to write it as 2 angle 45 degrees, okay. Very simple. Now I can write V, so it's still a simplification of this guy, V20 ohms by 20 ohms, okay, plus V20 ohms by J10 ohms. That's this guy. Okay. What else? Minus V20 ohms. If you factor that out, you're going to have 10 by 20, okay, by J10 ohms equals to 2 angle 45. I'm not going to do a lot of mathematics here. I'll just show you that the final result is once you simplify, factor out all the common terms, you can factor out V20 ohms by 20 ohms, okay? Then you will be left with 1 plus 1 by J, which is 1 by 1 minus J1, okay? Equals to 2 angle 45 degrees, okay. And then you'll see that V20 ohms by 20 ohms, which is really Ix, you'll find that it's equals to square root of 2 times 2 angle 90 degrees, okay. 2 angle 90 degrees. What is this? This is the expression that you would get for Ix, okay. So all I have done is to apply KCL at node N1 and then followed simple mathematical analysis. Okay, simple mathematical analysis here. What else you got? The other thing is we are interested in calculating VTH here, right? VTH. If you think about it, look at this. There is a voltage of 10 Ix being applied here, and that is divided among these two impedances. So I can use a voltage division to find out V Thevenin, which is dropped across this impedance. Okay, the voltage using voltage division. So I'm going to put my voltage division hat on using voltage division to calculate V Thevenin. Okay, in order to calculate V Thevenin, I'm going to see that the V Thevenin is actually the voltage division between negative J10 ohms and 10 ohms. Okay, all right. So let's write that out, or maybe, you know, just copy this so that we have it in front of our eyes. Okay, so voltage division, we are interested in calculating the voltage there. Okay, how do you calculate that? Using voltage division to calculate VTH, you will see that V Thevenin equals to negative J10 by negative J10 plus 10 ohms. So this plus this. Simply a voltage division problem. Okay, times let's not forget the um, current that's going there times times the 10 times Ix, because that's the voltage that's being applied. This voltage 10 times Ix is being divided between the capacitance and the resistance, and the voltage division is this guy. Okay, now what we can really do is that once we have Ix, Okay, we can plug in. We do have Ix though. Ix is what? Square root of 2 angle 90. Square root of 2 angle 90 degrees. We found that out from the KCL, right? So we can plug that in here. Okay. Now all we have to do is V Thevenin equals to negative J10 by 10 times. So I'm going to factor out 10 all over negative J by negative J plus 1. Okay. So that's going to be times 10 Ix. So plug in the value. Negative J is what? 1 angle negative 90 degrees. 1 minus J is square root of 2 angle negative 45 degrees. And then of course 10 times. Ix is what? Square root of 2 times 2 angle 90 degrees. So it's just a matter of doing your polar multiplication. So this 1 multiplied by 10 is 10 square root of 2. Negative 90 plus 90 is what? 0. Okay. So V Thevenin therefore equals to 10 square root of 2 angle 0 divided by 2 angle 45. Square root of 2 angle negative 45 degrees. So you have 10 angle 45 degrees. That is your V Thevenin. 10 angle 45 degrees. Okay, but that's just one part of the problem. You see, we are supposed to calculate V Thevenin. We did calculate 10 angle 45 degrees. But how do you calculate Z Thevenin? Let's see if we can do something about it. Let's see if we can apply some technique to calculate the next part, which is a Z Thevenin. Okay, I'm going to clean the, oops, I'm going to clean this up a little bit. Okay, now to calculate Z Thevenin, the first thing I want to do is to deactivate the independent current source. All current sources you want to open circuit them, and all voltage sources you want to short circuit them. Okay, so that's, let me leave them here. Okay, there. So the current source is deactivated. That's done. Now what do? Now we want to apply a test voltage, test current method. Okay, apply V test and look at I test. So that's what I'm going to do. I'm going to apply a V test and get an expression for V test over I test. So I'm going to look at V test and I test. Okay, now I'm going to do KVL around the leftmost loop, left hand side loop. Look at this loop. Okay, let's look at that loop and let me see. I don't want to forget that this guy is given to be Ix. It's given. Okay, um, that's Ix. Now, if I apply KVL around the left hand loop, okay, if I apply KVL around the left hand loop, start at the bottom left, go around. the loop, I have a negative Ix times 20 ohms, okay, plus negative Ix times J 10 ohms, and then plus 10 times Ix equals to 0. Okay, now I can factor out Ix. When I factor out Ix, what I have is negative 10 ohms, negative J 10 ohms. All of that equals to 0, which means Ix equals to 0. Very important result here because it's going to have important consequences. Let me copy this. In this circuit, if Ix equals to 0, think about this. The voltage drop here goes away. The voltage drop here goes away. Okay. And what else is going to happen? You see, when Ix is 0, this drops to 0. Okay. So what you are left with is something that looks like this: 10 ohms, negative J 10 ohms, and then V test going, I test going in. This guy, a pretty convenient simplification. Okay, this is 10 ohms. This is negative J 10 ohms. You see, they're both in parallel. So V test or I test is really V test times the parallel equivalent of this negative J 10 ohms plus 1 over 10 ohms. Okay, you see, V equals to IR or IZ. I equals to V times R inverse. Okay, so you don't need an additional inverse here for the parallel because two inverses cancel out each other. Think about it. Okay, so we are interested in calculating ZAB. Okay, ZAB, which is the AB, the impedance at these two terminals, which is given by V test over I test. Okay, V test over I test therefore is 1 over all of this, 1 over negative J 10 ohms plus 1 over 10 ohms. You can simplify that. You will see that it is 10 by 1 plus J. That's the Z Thevenin, which is the same as ZAB. Okay, which is going to be 10 by 2 angle 45 degrees. Therefore, Z Thevenin is really 10 by square root of 2. Let me see, square root of 2, which is 7.071 angle negative 45 degrees, or that's equals to 5 minus J 5 ohms. Therefore, that solves the problem in its entirety. V Thevenin, we found that out to be what value did we get for V Thevenin? 10 angle 45, 10 angle 45 degrees, and Z Thevenin is 7.071 negative 45 or 5 minus J5 ohms. So that is the complete description of the Thevenin equivalent circuit and hence the answer.